Welcome to Quantum Realms Explained. Today, we're diving into a fundamental question. Why do we need quantum physics? We'll explore the limitations of classical physics and how they paved the way for a revolutionary understanding of our universe. For centuries, classical physics, primarily based on Isaac Newton's laws, provided an incredibly successful framework for understanding the physical world. It brilliantly described the motion of objects, from falling apples to orbiting planets, and explained everyday phenomena like gravity and forces. Classical physics excelled at predicting the behavior of macroscopic objects and systems with remarkable precision. From designing bridges to launching rockets, its principles were indispensable. However, as scientists probed deeper into the subatomic world and extreme conditions, classical physics began to show cracks. It couldn't explain everything they observed. One of the first major puzzles was the black-body radiation problem. Classical physics predicted an infinite amount of energy at short wavelengths, a phenomenon dubbed the, quote, ultraviolet catastrophe, which clearly didn't match experimental results. Another perplexing phenomenon was the photoelectric effect, where light striking a metal surface could eject electrons, but only if the light had a certain minimum frequency, regardless of its intensity. Classical physics couldn't explain this threshold. The very structure and behavior of atoms also posed significant challenges to classical physics. Rutherford's model of the atom, with electrons orbiting a nucleus like planets around a sun, classically predicted that electrons should continuously lose energy and spiral into the nucleus, leading to atomic instability. But atoms are stable. Furthermore, when atoms are excited, they emit light only at specific, discrete wavelengths, producing unique spectral lines. Classical physics predicted a continuous spectrum, failing to account for these distinct, quote, fingerprints of elements. These profound failures of classical physics at the microscopic level signaled the need for a completely new theoretical framework. This marked the birth of quantum mechanics. In 1900, Max Planck introduced the revolutionary concept that energy is not continuous, but emitted and absorbed in discrete packets, or quanta. This groundbreaking idea, initially a mathematical fix for black-body radiation, laid the foundation for quantum theory. Building on Planck's work, Albert Einstein proposed in 1905 that light itself consists of discrete particles called, quote, photons, to explain the photoelectric effect. This was a radical departure from the classical wave theory of light. These ideas led to the concept of wave-particle duality, where particles like electrons and light can exhibit both wave-like and particle-like properties, depending on how they are observed. This duality is central to quantum mechanics. Another cornerstone of quantum mechanics is Heisenberg's uncertainty principle, which states that it's impossible to simultaneously know with perfect precision both the position and momentum of a particle. The act of measuring one affects the other. Beyond these, quantum mechanics introduced mind-bending concepts like superposition, where a particle can exist in multiple states simultaneously, and entanglement, where two particles become linked, influencing each other instantaneously regardless of distance, a phenomenon Einstein famously called spooky action at a distance. So why quantum? Because classical physics simply couldn't explain the fundamental behavior of matter and energy at the atomic and subatomic scales. Quantum mechanics provided the tools to understand atomic stability, discrete spectra, and the perplexing nature of light and particles. Quantum mechanics is not just a theoretical curiosity. It underpins much of modern technology, from lasers and transistors to medical imaging and quantum computing. It represents a profound shift in our understanding of reality, revealing a universe far more complex and fascinating than classical physics ever imagined.